Welcome everyone. Today let's study modern periodic law and structure of the modern periodic table. Alright, and this is from lesson periodic classification of element and part 4 video of this lesson for class 10. Let's begin. Alright, now let's study about modern periodic law. Student, the scientific world did not know anything about interior of the atom when the Mendeleev put for the periodic table. Alright, and we know that the structure of an atom inside the nucleus, it contains positively charged proton and neutrally charged neutron, and around the nucleus electrons are revolving in a negatively charged electrons are revolving around a particular orbit. Okay, so after the discovery of the electron, scientists started exploring the relation between the electron number of an atom and the atomic number. So student, what is the relation between electron number of an atom and the atomic number? So the number of electron which are negatively charged in a neutral atom is equal to the number of proton that is positively charged particle. Okay, that means number of electron is equal to the atomic number. All right, and the atomic number is in Mendeleev periodic table only indicated the serial number of the element. That means atomic number in the Mendeleev periodic table is only indicated the serial number, it is not indicated the number of a proton or number of a electron. All right. Okay. So in 1913 AD, the English scientist Henry Moseley demonstrated with the help of the experiment done using X-ray tube that the atomic number, which is represented by the Z of an element, correspond to the positive charge of the nucleus or the number of a proton in the nucleus of the atom of that element. That means atomic number is nothing but equal to the positively charged proton which are there in the nucleus of an atom. All right, and this revealed that atomic number is a more fundamental property of an element than its atomic mass. So student, we have completed different theories or different law related to the periodic table, but this is this periodic table, which is Henry Moseley periodic table, it is more acceptable. Why? Because this is related, because this says that atomic number is more fundamental property of an element than its atomic masses. Okay, so atomic number is a number of a proton. All right, and atomic mass is the weight of an atom or mass of a particular element. And the law, okay, accordingly the statement of the modern periodic law was stated as follows, that is, properties of elements are a periodic function of their atomic number. That means properties of an element, that is physical and chemical properties of elements, are nothing but related to the atomic number. That is, atomic number means number of a proton present in the nucleus of an atom. So this is about the modern periodic law by Henry Moseley. Alright, now let's understand the modern periodic table, which is a long form of the periodic table because it contains most of the element, that is 118 elements till now. Okay, so this is also known as a long form of the periodic table. So student, the classification of elements resulting from an arrangement of the elements in an increasing order of their atomic number is the modern periodic table. Okay, so you can observe here the structure of structure of the modern periodic table, in which you can observe that total 118 elements are there, and these are arranged in according to the increasing order of their atomic number, that is increasing number of the number of proton inside the nucleus of a particular element. All right, and the properties of elements can be predicted more accurately with the help of the modern periodic table form on the basis of the atomic number. So here the elements which are present in the modern periodic table, their properties can be easily or well predicted. Why? Because these are arranged on the basis of increasing order of the atomic number. Alright, and the modern periodic table is also called the long form of the periodic table because it contains 118 elements till now. You can observe here first element is hydrogen and last element is 118, that is UUO. Alright, Now student, in the modern periodic table, the elements are arranged in accordance with their increasing order of the atomic number, which is related to the number of a proton in the nucleus. And as a result, most of the drawbacks of the Mendeleev periodic table appear to be removed. Why? Because Mendeleev periodic table, in Mendeleev periodic table, the elements are arranged in an increasing order of their atomic masses. Okay, but here in modern periodic table, the elements are arranged in increasing order of their atomic number. Alright, and therefore all the drawbacks of Mendeleev periodic table have been removed in the modern periodic table. And however the ambiguity however the ambiguity about the position of hydrogen is not removed even in the modern periodic table. So student, in Mendeleev periodic table also the ambiguity about the position of a hydrogen is present. That means whether the hydrogen should keep in the group of alkali metals or in the group of halogen. So this ambiguity or this confusion is continued in modern periodic table also. Alright, so student, we have studied in the previous standard the electronic configuration of an atom. Now what does it mean, electronic configuration? This is the distribution of an electron in a particular shells of an atom around the nucleus. Okay, is determined by the total number of electrons in it, and the total number of electrons in an atom is same as the atomic number. That means the negatively charged electron number is equal to the number of a proton in an atom. Alright, so here alongside you can observe the atomic structure of the sodium element. Alright, sodium atom. So here the electronic configuration of as the atomic number is 11 of a sodium. So electronic configuration, that is distribution of electrons in an orbits, that is KLM, is 281. That means first shell of a sodium contain 2 electron, and second shell of a sodium contain 8 electron, and the last shell, that is a valence shell, it contain only 1 electron. Okay, so this is the electronic distribution of electron in the shells of an atom. And the relation between the atomic number of an element and its electronic configuration is clearly seen in the modern periodic table. Alright. Okay, now student, let us understand the structure of the modern periodic table, which is a long form of the periodic table which contain total 118 elements till now. Okay, student, now let us learn about the structure of the modern periodic table, which is the long form of the periodic table. Okay, so student, the modern periodic table contains 7 horizontal rows called as the periods from 1 to 7. Okay, so this is the structure of a modern periodic table, and here similarly the 18 vertical columns in this table are the groups 1 to 18. So you can observe here I mentioned with a black mark 1 to 18 vertical columns are known as the groups, and 7 horizontal periods are known as the horizontal rows are known as the period. That is from 1 to 7 periods, and 1 to 18 the vertical column, these are the groups of a periodic table. Okay, so these are the periods, and vertical are indicated by the groups. Alright, so the arrangement of the periods and the group result in the formation of a boxes, and atomic number are serially indicated in the upper part of this boxes. You can observe here I have mentioned red with the boron element. Okay, so in upper part of the boron it is atomic number is written, and B is a symbol for boron, and below, that is 10.806, this is atomic weight of a element, that is boron. Okay, so each box correspond to the place of one element. So there are total 118 boxes are there in the modern periodic table, and in each boxes one element is present. Alright, so student, apart from these 7 rows, 2 rows are shown separately in the bottom of the periodic table. Okay, so these rows are known as which are mentioned separately in the modern periodic table. These are lanthanide series, like a purple elements with purple, these are the lanthanide series, and down it is a red colored element, this is the actinide series. Okay, these are the separated series of a periodic table, that is lanthanide series and actinide series. Alright, and there are 118 boxes in the periodic table, including the 2 series. Okay, that means including lanthanide and actinide, there are 118 boxes are there in the modern periodic table, and it means that it and there are okay, and it means that there are 118 places for elements in the modern periodic table, and very recently formation of a few elements was established experimentally, and thereby the modern periodic table is now completely filled. That means last element you can observe here 109, 110 and 111 and 113 up to 118. These are the newly discovered elements formed just now, and these are completely filled. 118 places are completely filled now. Okay, so student, here you can observe the periodic table, and the entire periodic table is divided into 4 blocks, that is S block, P block, D block and F block. Alright, so S block contain 1 and 2 group. You can observe here, that is 1 and 2 groups contain, it is represented by S blocks, and on the right hand side it mentioned as P block, which is 13, which contain 13 to 18 groups. Alright, so right hand side P block and left hand side S block, and in the middle of S and P block, D block is there, which contains 13 to 12 groups. Okay, which contain 13 to 12 groups, and last is the it is D block, and last is the F block, which contain lanthanide and actinide series. At the bottom form the F block, and the D block elements are called as a so the D block elements are called as a transition element. Why? Because they have partially filled d orbitals. Okay, partially filled d orbital. That's why D block elements are called as a transition element, and student F block are called as a inner transition element, because they contain partially filled or halfly filled last orbital, that is F orbital. Okay. Alright, and the student, the 3 traditional types of elements can be clearly shown in the modern periodic table with the help of a zigzag line. You can observe a zigzag line and the elements which are lie just along the zigzag line, that is boron, silicon, germanium, antimony, okay, polonium and all. These elements are separated by the zigzag line, and the metalloids, okay, the metalloids element lie along the border of the zigzag line. Just measure, you can observe here, it is the metalloids elements are mentioned with the green color, okay, like boron, silicon, germanium, antimony, like this. And these are the metalloids element which contain the property of both, that is metal as well as non-metals, and all the metals lie on the left side lie on the left side of the zigzag line, while all the non-metals lie on the right side of the zigzag line. Alright, now student, let's understand modern periodic table and electronic configuration of an element. Okay, so within a period, the neighboring elements differ slightly in their properties, while distant elements differ widely in their properties. So I mentioned lithium and beryllium, which are neighboring elements, so their properties will be similar. Okay, but as we move from left to right, that is from sodium to argon, the properties will be dissimilar. Why? Because these are the very distant in the periodic table. So properties of the sodium, which is an alkali metal, will be differ from the inert gases, which is an argon. Okay, so this property will be dissimilar. And student, elements in the same group show similarity and gradation in their properties, and these characteristic of the groups and period in the modern periodic table are because of the electronic configuration of the element. And it is the electronic configuration which is the distribution of an electron in a particular orbit of the element which decides the group and the period in which it is to be placed. So this is the relation between so this is the modern periodic table and electronic configuration of an element. All right. Okay, now let us understand groups and electronic configuration. Okay, so student, what are the groups? These are the these are the 18 vertical columns in this periodic table from 1 to 18. Okay, so these groups are vertical columns. So student, here I have mentioned the electronic configuration of the alkali metal, that is group 1 element. Okay, and you can observe here the valence electron in all these elements from the group 1 is the same, that is from lithium to francium, lithium, sodium, potassium, rubidium, cesium and francium. The electronic the valence electron are the electron which are there in the last shell or valence shell. Okay, so it is same, that is each element contain one valence electron in its valence shell. Okay, and similarly, if you will observe the group 2 element which represent the alkaline earth metal from beryllium to from beryllium to radium, it is also containing 2 valence electron in the valence shell. Okay, so similarly there are 7 electron in the outermost shell of the elements such as fluorine, chlorine from the group 17, that is family of a halogen. Okay, so family of a halogen, the electronic valence shell in the element is same. Okay, that means each contains 7 electron in their outermost shell or valence shell. Alright, now student, you can observe here while going from top to bottom. Okay, so while going from top to bottom within any group, that is any group from 1 to 18, one electronic shell gets added to at a time, and from this we can see that the electronic configuration of the outermost shell is characteristic property of a particular group. And like you can observe here, the electronic atomic structure of a lithium, sodium and potassium elements, that is each shell is increasing, is added. Okay, by going from top to bottom, that is lithium, sodium, potassium. In lithium 2 shells are there, in sodium 3, and potassium 4 shells are present. So this is how the electronic configuration is increasing. Okay, and however as we go down a group, the number of a shell goes on increasing. Okay, now next is periods and electronic configuration. Now periods are 7 periods, like these are the horizontal, okay, horizontal row called as a period. So the number of a valence electron is different in these elements. Like you can observe here, you will find that the number of a valence electron is different in these elements. Like from lithium, beryllium, boron, it is period 2 elements. Okay, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. The the number of a valence electron is same. Alright, and however the number of a shell is number of a valence electrons are different, but number of a shells are same. That means each element contains 2 shells, only 2 shells. Okay, but the number of electrons are increasing. Like in lithium it is 1, and as we move from left to right, the electrons are increasing from 1 to 8. Okay, and neon contain 8 electron in its large shell, and lithium contain only 1 electron in its large shell. That means number of electrons are increasing while moving from left to right. Okay, so you will also find that while going from left to right within the period, the atomic number increases by 1 and at a time, and the number of a valence electron also increases by 1 at a time. Okay, so student, this is that's it for today's video. I hope you all have understood the long form modern periodic table and the long form of a periodic, which is a long form of the periodic table. So I hope you all have understood. That's it for today's video. Thank you.